second speaker is Shahid.
Hasan Shahid.
Hasan
Mohammad.
Shahid. So,
yeah.
Please let's start.
Bismillahirrahmanirrahim. Good morning to you all. The topic of my talk is B Y Chen Inequalities for statistical submanifolds in sasakian statistical manifolds. Basically, this is a joint work with Professor Michel Boyom and my student Mohammad Aquib and with Professor Alkhaldi from King Khalid University, Saudi Arabia. Before I start, I must be thankful to Professor Michel Boyom, who introduced a statistical manifold in 2015 when he visited our department, and since then I am trying to learn this statistical manifold, trying to do something, and I have published some paper I will show in the slides. So, before I give you the details in brief, I must give you a background of this problem. In 1993, Professor Chen published a paper on pinching theorem and classification of minimal submanifold. That was a fundamental paper, and he gave applications of that pinching result, means inequalities, in many areas of mathematics perhaps. Since then, many people started working on inequalities based on Chen's inequality, and this inequality is so famous, so popular, that it is named as B Y Chen inequalities. So, people worked in B Y Chen inequalities for different type of submanifolds, maybe totally real submanifold, CR submanifold, there are many in different ambient spaces. My intention is to see this type of inequality in a statistical setting. So, this is my idea. So, first I will discuss some statistical manifold and submanifold, then statistical submanifolds of sasakian statistical manifolds, inequalities in terms of extrinsic and intrinsic invariants, and then B Y Chen inequalities for statistical submanifolds in sasakian statistical manifolds. Since we had already many talks on statistical manifolds, I will not spend my time in this because already we know background. This is Mali's fundamental paper, book in fact, differential geometric methods in statistics, published in Springer Verlag. Then we have the definition as usual, that let M bar G be a Riemannian manifold with nebula bar affine connections on M bar, then a pair nebula bar G is called statistical structures if this condition is satisfied, and nebula bar and nebula conjugate, these are two torsion free affine connections on M bar such that this holds. Then we say that this M bar G is a statistical manifold, and we denote by this M bar G with these two connections basically. We have all these things. Now, let us take n dimensional submanifold of 2m plus 1 dimension manifold, and we have usual formula for Gauss formula, nebula bar x y is equal to nebula x y h x y, where nebula bar is the connections on ambient manifold and nebula is connection on this submanifold. H is second fundamental form. For the dual, we have this formula with a statistic, okay, and then we have basically the very useful formula known as Gauss equation, giving curvature relation between curvature of submanifold with curvature of the ambient manifold in fact. Okay. With the dual, we have this, as we have seen here, that R bar, you see R bar is equal to R x y z w plus h x z h stick this thing, and here, and for when we take R stick, then dual comes here in fact. Okay. So, So, when we have R strict, then dual comes here, R strict x y z w, g of s strict x z h of y w, and these things. Now we have this important formula, which is known as Lingandra Formula, where x is in the tangent bundle, n is normal bundle, then nebula x n is equal to minus a n x star x plus nebula perp x n, in fact, okay, where a is called shape operator and nebula perp is the connection in the normal bundle. The first paper which was published on submanifold, statistical submanifold, was in 1989 by Gauss, in fact, fundamental equations for statistical submanifold, in fact, 89. Then Professor Furuhata basically worked on a statistical hypersurface in a space of Hessian curvature 0 and provided some examples also. And then in 2017, Furuhata and his collaborators worked on, in fact, sasakian statistical manifold. So, this is generalized Windingen inequality for statistical submanifold and statistical manifold with constant curvature by Aydin Mihai and I Mihai. Then Furuhata, the same paper, hypersurface in statistical manifold, differential geometry applications in 2009, 17 also we have a paper. And then Milijevic, I think she is a student of Professor Furuhata. She did totally real statistical submanifold. And then Takano, Professor K. Takano published paper statistical manifold with almost contact structures and its statistical submersion appeared in Journal of Journal of Geometry. And then Vilcu from Romania worked on statistical manifolds with almost quaternion structures and quaternion Keller like statistical submersions, fact, appeared in Entropy. This is the paper by fundamental paper of B Y Chen, some pinching and classification theorems for minimal submanifolds, appeared in 1993, in fact. Now, let us go for almost contact metric manifold, means odd dimension manifold. Let us m bar be an odd dimension manifold. Let us take 2 m plus 1 and phi be a tensor field of the type 1 to 1, xi is a vector field, eta is one form on m bar satisfying these conditions, in fact. Then we say that this m bar is to have almost contact structure phi xi eta, in fact. And this is the definition of sasakian manifold, of course, in a statistical setting also, and almost contact structure phi xi eta on m bar is said to be a sasakian structure if this connection is satisfied. Then we have this nebula bar g phi xi is called sasakian statistical structures on m bar if nebula bar g is a statistical structure and g phi xi sasakian structure, and this formula holds where k is the difference tensor. Now, this is the basic curvature tensor formula for sasakian manifold of constant phi sectional curvature C. So, let m bar nebula bar g phi xi sasakian manifold with C is a number, real number, then sasakian statistical structure is said to be of constant phi sectional curvature C if the curvature tensor S bar is given by this C plus 3 by 4 with this term plus C minus 3 by 4 with this term, where S bar is nothing but half of R bar x y z plus R strict x y z. Now, let us take because we have some manifold of dimension n. So, the tangent bundle or we can say tangent orthonormal frame consists vector E1 to En, where En is equal to xi also, because there is xi also in also, and then En plus 1 up to 2m plus 1 is basically the normal orthonormal frame. With the help of these frame, we have the definition of mean curvature vector field with respect to H strict and H naught given by this, in fact, which is called mean curvature. For H strict we have this, and for H naught we have this, in fact. Now, in the conclusion we have some term like summation G of H E I E j H E I E j, we substitute this as a squared norm of secant fundamental form, and for H strict we substitute as a square norm of H strict in fact. Similarly, for H naught we have this thing. Now, having this H strict and this all these thing, we have some definitions of different types of submanifold. Like a submanifold is said to be totally geodesic submanifold with respect to nebula bar naught, respectively this and this if the secant fundamental form H naught respect to this thing vanishes basically. Similarly, a submanifold is said to be minimal submanifold with respect to this connection, respect to all these connection when mean curvature vector H naught, similarly H and S vanishes basically. Okay. Now, let K pi be the sectional curvature, and we have already framed E1 to En and orthogonal frame for TPM, and we have framed En plus 1 to E2n plus 1 for the orthogonal frame for the Normandel. We defined as a scalar curvature tau p at the point P like this in fact. Similarly, normalized scalar curvature rho is defined like this. Now, we substitute for G of H E I E j E gamma, where E I for I and j runs in the tangent bundle 1 to n, and gamma runs from is in norm bundle in fact. Means E gamma means E n plus 1 is in norm bundle in fact, and we substitute this as H I j gamma. Similarly, we have substituted H I strict gamma for strict. Okay. Now, we have some more papers on inequalities like curvature inequalities for Lagrangian submanifold and different geometry applications, and then the same paper we have earlier mentioned, and then Özgür Mihai in fact published paper chain inequalities for submanifolds in real space form with semi-symmetric connections, appeared in Canadian Math Bulletin in 2012, and this is Shahid and Nguiffo paper inequalities for cathodic curvature for slant submanifolds in quaternion space form, appeared in Journal of Inequalities and Applications. Now, we have to shift, and now there are some more papers on inequalities like Murathan and B Shahid just published a paper in 2018 entitled A Study of Windigan like inequality for submanifolds in statistical wire product manifolds. And my student Aquib has published just a paper in 2019, some inequalities for statistical submanifolds of quaternion Keller like statistical space form, appeared in International Journal of Geometric Methods and Modern Physics. Now, let us come to the main point, main result. Now, what we have, let M be a statistical submanifold in a sasakian statistical manifold M bar C with this condition. We have this condition. To make the calculations easy, we have substituted H11 strict and H22 plus H11 H22 strict as this thing, means this thing minus this thing is 0, such that the structure vector field xi of M bar C, where M bar C is sasakian space form, is tangent to M, means xi is tangent to M. Okay. Then we have this inequalities K pi is less than or equal to tau and all these things, means this is the relation between sectional curvature and scalar curvature, where we have in the calculation we have substituted G square phi E1 E2 as pi p theta pi, and then eta square and E1 eta square 2 we have substituted phi pi, and G square phi E1 phi EI EJ we have substituted in the calculation as a square of norm p.
Excuse me. Sorry, I missed. What is K? K is sectional curvature. What kind of sectional curvature? Repeativity or phi sectional curvature?
Phi sectional curvature.
Okay.
Now, using you see, sorry. Using this expression of 9 for S C plus C by 4, we have after calculations we have this thing in fact G of R x y z w plus G of R strict this thing is given by 2 and 2. Because we have to find sectional curvature, means we have to take care of basis element. So, we substitute y as y w as E I and z x z as E j in this equation, and after calculation we get in fact this 24. Then using the relation that h plus s strict is equal to 2 times h naught, we have used this in fact equation in this calculation, and we get in fact 25. On the other hand, sectional curvature can also be obtained by the formula like half of g of r plus g of r strict, and then using the coefficients r strict, we have this thing, and then taking inner product with w in 9 in basically the same thing, same equation, we have these equations. So, g of s star E 1 E 2 E 2 E 1 is given by c plus 3 by 4 plus c minus by 4 of this term in fact.
Sorry, excuse me, I'm confusing.
Yeah.
What is the difference k and s bar? S
bar is defined as you see, sorry.
Phi sectional curvature. So
yes, s bar is equal to this r plus.
What is k?
What is k? What is
K?
K is a sectional curvature in fact, expanded by E1 E y E j.
K is sectional curvature
with basis element E I and E j in fact.
Okay.
Yes. So, having these things now we have 25 equations, and then on the other hand we have k pi like this, taking inner product with w in that same equation 9, which gives c plus c by 4 all these things, and putting the value of x w as E 1 y z as the E 2, we have this equation last, c plus c by 4 plus c minus by 4 and this thing in fact. So, we get this 2 k pi in this form, and then take the difference of in fact 25 and 28. Okay, we have 2 k pi minus 2 rho is given by this thing. Okay. Now, because we have to have inequalities, till now we do not have inequalities. So, to get inequalities, what we use? We use this in fact, a square of h plus h strict norm is given by this, and then expanding by this, what we get? We get inequalities, a square of norm h plus a square of norm h strict is given by this in fact. Using this inequalities in the above, where here what we have this 2 k pi minus 2 gamma is less than or equal to plus 3 c plus 3 by 2 this thing. We have explained what is p and what is the theta pi, and in fact phi pi already we have substituted the value, already explained earlier. Then we have this thing, we got this thing. See, earlier we have this thing plus this term, but this term is 0 because of our assumption in fact. We have assumed that this thing is equal to this thing, 0 in fact. So, from this and using our hypothesis, we got this inequalities. So, this is the final inequalities which we call as B Y Chen inequalities for any submanifold, not in particular, any submanifold of sasakian space forms in fact. Now, we have some particular case, like let M be a statistical submanifold in a sasakian statistical manifold M bar C with this condition as usual, such that xi is tangent to M, then we have this thing. But if M is totally geodesic, it means that H is 0. See, earlier what we have term in terms of H here. So, when M is totally geodesic means this vanishes in fact. So, what we have now? We have now only this term, means k pi minus 2 is less than or equal to this thing, okay, except H, because H is 0 because of totally geodesic submanifold. Similarly, when we take the a structure vector field xi of m bar c as normal. In fact, in normal case what happens, eta comes which comes appears in the coefficient will be 0, because eta x means g of x xi. Xi is normal, x tangents in will be 0. So, by taking xi to be normal to submanifold, the term appearing in as eta will be 0, and we have this thing after calculation we get this thing in fact. Similarly, so what happens again, because xi is normal to submanifold, we do not have eta terms, we have some different terms like this with this term. Again, if the submanifold is totally geodesic, again this h is 0. So, in this case we have this result in fact. So, let M be a statistical submanifold in a statistical sasakian statistical manifold M bar C with this condition, such that xi of M bar C is normal to M. This holds if M is totally geodesic with respect to this in fact. So, now we have some conclusion that this type we have worked for a special type of submanifold, a special type of ambient manifold, Sasakian manifold with constant phi succession curvature. We mean Sasakian space form. Now, this type of inequality can be obtained, can be seen in different types of ambient manifold, like holomorphic statistical manifold, Kenmasu statistical manifold, co-symmetric manifold, and quaternion Keller-like statistical manifold. So, this type of inequality can be seen in terms of in ambient manifold like this in fact. Now, we have some references. This we published generalized normalized delta cathodic curvature in for statistical submanifolds in quaternion Keller-like statistical space form, appeared in General Geometry in 2018. Now, this is basically last year paper, generalized Weintraub type inequalities for Lagrangian submanifold in holomorphic statistical space forms, okay, in GSI 17, and this is the paper which we published on Salant submanifold in fact CR Science Paris, and Furuhata and Hasegawa, Okuyama and Sato and myself worked on Sasakian statistical manifold, appeared in General Geometry and Physics 2017, and this is basically a Furuhata paper which appeared in the book Submanifold, in fact volume, this is the volume, Submanifold Theory in Holomorphic Statistical Manifold. Basically, this is a contributor, in fact contributor volume published by Springer, editor Dragomir, myself and Saleh Sulumi. And then we have a paper, Ali Alkhaldi, Aquib, Ali Anaz, myself on pinching theorems for statistical submanifold Sasakian like statistical space form, appeared in 2018 in Entropy, and recently we published with my student Pooja Bansal, Sirajuddin, myself on the normal scalar curvature conjecture in Kenmasu statistical manifold, appeared in Journal of Geometry and Physics 2019, and this is the end.
Thank you. Are there any questions or comments? No. So, I have a question.
Yes,
so,
yes.
In statistical manifold theory, the notion of sectional curvature is not unique. So,
yes.
What is the motivation of phi sectional curvature, or what is the advantage?
See, there is a paper of Upazda.
Yeah.
I think the top title, I think sectional curvature also. The Upazda, I think.
Yeah, Upazda have introduced many kinds of
Sectional
sectional
curvature.
So, what is the advantage of phi sectional curvature?
Because when we have any manifold,
Yeah.
and if phi sectional curvature is constant,
Yeah.
then that forms a space form.
Okay.
And when we have space form, then many things known in fact. So, main thing is a space, to have a space form, and to get a space form, what we have to have manifold with some sectional curvature constant.
Yeah.
So, if phi sectional curvature is constant, then we get a space form.
Okay.
That is the idea.
Okay. So, let's thank the speaker again.